let's talk about cis and trans isomers. So your cis and your trans isomers, they are stereoisomers. Let's remind ourselves what stereoisomers are. They have the same molecular formula, same connectivity. There's a difference in the orientation of the molecules in space. You don't have to worry about in space. It's just how there's a different orientation, right? Now, your cycloalkanes, whether they're planar or in a chair conformation, right? Those with your cycloalkanes or your chair conformation with substituents on two or more carbons of the ring, in this case, two carbons of the ring, right? Substituents can show cis or trans isomerism. All right. So your chair or any cycloalkane that has substituents on two or more carbons of the ring can show cis or trans isomerism. Now, cis means same side, right? If you forget, just remember sister. Your and sister are supposed to be on the same side, we hope. All right. So cis, same side. Okay. So in order to this is how that's what I use to distinguish between cis and trans, right? Trans is opposite side, which means that the groups, right? So your substituents are on opposite sides of the ring. Trans mean opposite side, cis means same side of the ring. And like I said, cis sister is supposed to be on the same side. So your CH3s here are both below the ring, cis. CH3s here, one is above, one is below, trans. You could also look at the hydrogens here, right? There are cases where you'll use hydrogens. We'll talk about that when we get to alkenes. So cis, same side, right? Now let's talk about the fact that these two molecules that we have here are cis and trans isomers, which mean they're stereoisomers. So they have the same molecular formula. Their molecular formula is C7H14. You can go count it if you don't believe me. It's a total number of carbons. You would have learned this earlier in the chapter that has to do with molecular formula. I think that's the GenChem organic merge in order to help you. So you count the total number of carbons. So it's 5 carbons in the ring. 1, 2, 3, 4, 5. And then there's that. Then you can count the hydrogens yourself. It's C7H14. So we have the same molecular formula. The connectivity is also the same. I'm going to number the carbons over here. And I'm not numbering as if I were naming. I'm just numbering to explain to you. So remember, stereoisomers, same molecular formula, same connectivity, right? So let's prove that we have the same connectivity. I think the only thing that looks different in your eyes here should be these two, carbon 3 and 4, right? But let's look at carbon number 3. Carbon 3 here, right? The connectivity is the same because on carbon 3 I have a hydrogen, I have a CH3. On carbon 3 over here I have a hydrogen and I also have a CH3 bonded to carbon 3. That's how when you talk about connectivity, that's what we're talking about. What is on carbon 3? What is connected to it? It's this, and then it's the CH2, this carbon with H and CH3. Same thing over here. Hydrogen, CH3, CH2, carbon with the hydrogen and CH3. So the connectivity is the same. What's different is the orientation, right? The orientation on every carbon except for 3 and 4 is the same. The orientation on 1, 2, and 5, they're all the same. But when you look at 3, in the cis molecule, the hydrogen is above, the CH3 is the same. Sorry. On carbon 3, the orientation is the same. Sorry, the orientation is different on carbon 4. If we look at carbon 4, we see that we have a hydrogen and a CH3. The CH3 is at the bottom, hydrogen at the top. Here, the CH3 is at the top, the hydrogen is at the bottom. So these are two stereoisomers. Same molecular formula, connectivity is the same all around. The difference is in the orientation of the H and the CH3 at carbon number 4. So yes, they are stereoisomers. They are specifically called cis and trans isomers, or we also call them configurational isomers, because the configuration at a particular atom is different. So they're also called configurational isomers, right? So just remember, cis same side, trans opposite sides. Now, what if you were asked to draw the chair conformation for cis 1,2 dimethyl cyclo, one word, cyclohexane. So you're just asked to draw the chair conformation for this. Pay attention, it said cis, right? Now to do this, it doesn't matter which chair conformation you draw. Remember, we have two chair conformations. You're just asked to draw, right? Not stability, just draw. So any chair you draw here is fine. I need to point out something to you when it comes to your chair. Cis and trans has nothing to do with axial and equatorial. This is what I mean by that, right? If a bond, if two bonds are axial, does not mean, does not tell you that it's cis. If two bonds are equatorial, does not mean that it's cis. It's all about the position. It's all about the position. If the two bonds are up, whether axial or equatorial, that is what makes it cis, whether they're on the same side. If the two bonds are down and they're both axial, then yes, they are cis. Remember, axial and equatorial has nothing to do with cis and trans. It's all about if both of them are above, up or above the ring, and if both of them are down or below the ring. That's how you get cis, right? If it's trans, if one is up and one is down, whether axial or equatorial, then it's trans. Okay? Great. So let's draw a chair. Let's draw cis 1,2 dimethyl cyclohexane. I already have a chair drawn, so let me bring it up. Don't worry, if you forget to draw how to draw chairs, just go back to the video on drawing chair conformations. So we're drawing cis 1,2 dimethyl cyclohexane. Your ring portion is the cyclohexane portion. It's 6 carbons in here, right? 1, 2, 3, 4, 5, 6. That's the cyclohexane portion. On carbon 1 and 2, I have 2 methyl groups. Now, it's your chair. You can put your methyl groups wherever you want. They just need to be next to each other. So I like to stay on the nose. So I'm gonna put my carbon 1 here, right? For carbon 2, you could have either gone here or here, okay? I'm going to put mine here. Notice what I did, by the way. I put in my axial and my equatorial bond. This is my axial bond. I know it points down because these lines here meet pointing down. Wherever the lines meet pointing is where your axial bond points. If my axial bond is down, the other bond, which is equatorial, has to be up. One bond up, one bond down. If I go over here to this carbon, the two lines meet pointing up. That's where your axial bond points. So my axial bond here is pointing up. Equatorial is pointing down. Now, I put these bonds right next to each other because the molecule says 1, 2. So this is carbon 1. Let's use a light blue on the yellow. This is 1. That's 2. All right. It says cis, which means my, let me take these out. I just want to see everything. So, which means that my methyl groups need to be on the same side. Okay. So, if I put my CH3 here, it's down, right? It's axial down, which means when I put the other CH3 up here, it also needs to be down. This is down. It must be on the same side for it to be cis. So, the only bond down here is your equatorial. So that right there is, this right here is cis 1,2 dimethyl cyclohexane. Okay, both bonds are below the ring. I could also have done this. Either one of these would have been correct. if I had put my CH3 here on the bond that's up, right? When you move here, my CH3 needs to be on the bond that's up. The only bond up here is my axial. This is equatorial down. So up, this is up. Keep it up because it says they got to be on the same side. So your CH3 will be here. So either one of those would be correct. Let's draw trans. We're going to draw, that's not golden. We're going to draw trans 1, 4. So you have practice with both cis and trans. Methyl cyclohexane as a chair conformation. Before I draw that, we didn't name this, but I know you're a pro. You should be able to name this. It's 5 carbons in your ring, right? So that's cyclopentane, and these are on the same side. So it's cis 1, 2, cyclopentane. Remember, I didn't number. These numbers are not in order for your number. It was just for explanation. After we draw these, you should be able to go back and name that, right? All right, let's bring this chair up. Cool. Let's draw trans. So remember, trans mean opposite sides. Sister, cis is the same side. Trans is opposite sides. So it's trans 1, 4, 1, 4 dimethyl cyclohexane. Cyclohexane is taken care of. This tells me that on carbon 1 and on carbon 4, I have two methyl groups, right? Sorry. On carbon 1, I have a methyl group. On carbon 4, I have a methyl group. In total, I have two methyl groups. So let's draw that chair. And they must be on opposite sides of the ring, or both. One must be up, one must be down. So let's do this. I love to stay on the nose. So that right there is, I'm calling this carbon 1, right? And if this is my carbon 1, I need to count to have 4 carbons away, right? Because my other methyl group is on carbon 4. So I can go 1, 2, 3, 4. If you went in the other direction, 1, 2, 3, 4, you'd end up here, okay? So that's where my 4 carbon is. Axial bonds point up on this, point up, equatorial points down. Oh, too long. All right, so I have my carbon 1 and I have my carbon number 4. So that's 1, 4. All right. Now, it needs to be trans. All right. So let's say I put my CH3 here. It's down, right? Cool. Go over to carbon 4. I have an axial bond that's up and an equatorial bond that's down. My CH3 here is down and it must be on opposite sides. So if it's down, in order for this to be trans, my other bond has to be in the up position. So it got to be up and down, okay? It has got to be up and down, right? Has got to be up and down. Nothing to do, in this particular example, great, both of these are axial. That's cool. But remember, that is not what determines trans or cis. Because if you look up here, right, this is equatorial, that is axial. But they're on this, they're both up, so that's what makes that cis. So don't make that mistake, all right? This is trans. We could have also done this for the trans. If I had put the CH3 on in the equatorial position, right? That's equatorial, up. This is up, right? When I go over here, my axial bond is up and my equatorial bond is down here. CH3 is going to be here in the equatorial position. So up, down. You notice in this case, they're both equatorial, but because one is up, one is down, that's what makes it trans. So this is how you draw your cis and trans chairs. And if you have it in a planar, in like a planar cyclohexane, it's easy to see. It's about below ring, one above, one below. By the way, if both of these CH3s were above the ring, it would still be cis, okay? So cis and trans isomers are pretty simple.